So I'm a physicist, and I don't have any background in economics. But I think that this interface is a very exciting one. And I haven't quite formed a view on the question that's in the title of the meeting, can economics be a physical science? I'm still sort of imbibing what has been said here and sort of trying to form my own view. But just one thing that strikes me as being different between economics and physics, and that may have important consequences that need to be taken into account, is the question of the relationship between the microscopic degrees of freedom and the system as a whole. In physics, of course, we are used to the basic microscopic degrees of freedom. Eventually those degrees of freedom are fixed. They are quarks or electrons or atoms and so on, and the interactions between them are also fixed. There could be strong interactions, electroweak interactions, whatever they are, but they don't change with time. Whereas I think in economics, some of the most interesting phenomena perhaps have to deal with the fact that although we are talking of the same basic degrees of freedom, human beings, those are our microscopic degrees of freedom, so to speak. But the attributes of human beings that start to matter change with time. So, in hunter-gatherer societies, or in agricultural societies, or in colonial society, or in modern sort of societies, the attributes that matter are different. We would never talk about wealth, for example, in a hunter-gatherer society, or we wouldn't talk about maybe we could talk about wealth, but not in the same way, and we wouldn't talk about communication capabilities of individual agents in let's say 500 years from back, as we would talk about today. So the basic degrees of freedom that characterize the agents actually have changed with time, and the interactions between agents have also changed with time. And this is in part the stuff of innovation, that degrees of freedom and their interactions have changed with time, a feature that doesn't exist in physics. In physics, we don't have to contend with such kinds of things. Of course, there are effective degrees of freedom which come into existence in physics, and those change with time from system to system. Those are emergent degrees of freedom and so on. But as far as the basic degrees of freedom are concerned and their interactions are concerned, we are never in doubt about their constancy. So this is one thing, and so my talk will not address this basic question. I will talk about innovation, but still in a limited context, in fact in a very limited and narrow context, within the confines of a particular model, a mathematical model which is originated in physics, and it is supposed to be a model not of economic phenomena, but a model of the origin of life. And the origin of life, the origin of the first cell, for example, on the earth, is a problem that has many parts, and one of the parts of that problem is an organizational problem. A cell is a very complex organization of diverse kinds of molecules, and such an organization did not exist when the earth came into existence. Only after the oceans formed could molecules self-organize into something like a living cell. So a chemical organization emerged from scratch somewhere on the prebiotic earth, and this organizational transition is what I've been interested in capturing through various mathematical models. And in the course of this, so there is a mathematical model that I will describe, and the first part of the talk will be just the description of that model and the results of that model. it's a model of the evolution of a chemical network. We will see that the network structure changes with time, starting from a random network to a network that then starts to become non-random and grow in a certain sense, grow more complex. And so there is a growth of complexity, and then it reaches a certain peak and then sort of stabilizes there for a while. There is a stasis, and then there are crashes in the network complexity. So there are these events of growth, stasis, and collapse. And one can describe these things without reference to innovation at all, completely mathematically in the model. But what I would like to present is that one can also define the notion of innovation that seems appropriate for a model like this, and that seems to capture certain features of innovation that are, that transcend the model, the fact that growth and that innovation is very crucially sort of implicated in the growth and collapse of the system. So the work that I'll be talking about has been done primarily in collaboration with Sandeep Krishna, who was a PhD student at the Indian Institute of Science, and also partly in collaboration with colleagues Ravi Mehrotra and Vikram Soni, who were at the National Physical Laboratory in Delhi, and some work that I've been thinking about but haven't written up. So the first part of the talk will be just describing the model and its results, and then I will come to a definition of innovation in the context of this model, and then show you that some of the important events in this model are precisely related to innovation, both growth and collapse. So the model has a network as a dynamical variable. The network is characterized by an adjacency matrix C, whose matrix elements Cij are either 0 or 1. Okay? It defines basically Cij is equal to 1, defines a link from J to I. It's a directed graph. Okay? The graph has S nodes. S is the number of chemical species in a so-called prebiotic pond. Okay? Now this prebiotic pond, I mean, in a loose way, one might sort of extrapolate and think of an economic system in which each node, which here represents a chemical species in a pond, in a prebiotic pond, represents a firm, let's say, in an economic system. Okay? And each of these molecules, each of these nodes, of course, is possibly linked to the other nodes. And the link physically means, in the case of this chemical model, is that if there is an arrow from this node to this node, it means that the first node catalyzes the production of the second node. Right? So the presence of the first node in the pond causes the population of the target node of that link to grow with time. It catalyzes its production. Okay? That's the catalytic link. In the case of a firm, you might think of a link from one firm to another as a certain firm contributing to the well-being of another firm by providing it, let us say, with either raw materials or trained manpower or finance, sort of loan, etc. So that that's the catalytic link between one node and another. And the whole network is then a network of one thing catalyzing another, the other catalyzing others, and so on. The initial network in the model is chosen to be an evolutionary random graph in which links between nodes are drawn with probability p. With probability p, Cij is 1, and 0 with probability 1 minus p. And diagonal entries have been taken to be 0. There's no node which catalyzes its own production. Okay. Now, So this is basically the variable. This is the variable Cij will change with time, and this cycle tells you how it will change with time, and I'll describe that in a moment. But I should mention that there is another variable in the model, which is a fast variable, faster than the C variable, which is the actual populations of the nodes in the pond. So the idea is that every chemical species in the pond has a population, and the relative population of the ith species is what I will denote as xi. Okay, and I'll describe that more in the next slide. And there is a dynamics. So given the network is a slow variable, and the network, while the network remains constant, the populations change with time according to a certain dynamical equation, which I will describe later, which captures the fact that the catalytic dynamics, which captures the fact that if a catalyst is present in the pond, it has some non-zero xi or xj, then it can cause the population of whatever it is catalyzing to grow with time. Okay, so that kind of dynamics. Okay, that's the thing. And so the update rule for the network in the model is the following. And this xi, which is the population of the molecule for the catalytic scenario, in an economic scenario might be thought of as an overall well-being of a firm. Let's say its wealth or something like that, some measure of its well-being. Okay, so now so you start with a random network, and P is chosen to be small so that the network is quite sparse. Now, less than one link per node. Now, what happens is that the dynamics is as follows, that you allow the network to be fixed, and you allow the populations xi to evolve according to the equation that I will describe in the next slide. I will come to it. Let me not. Let me complete this story. So there is a certain population dynamic. C is fixed, the x's evolve, and they reach some attractor configuration. And in this attractor, some nodes will have large xi, some nodes will have small, some nodes will have large xi, small xi, etc. So different nodes will have different values, and those values will reflect what the network is. Who catalyzes whom will determine what the relative populations are. So some firms will do better, some firms will not do well. That depends on which firms are helping them and the relative well-being of those firms themselves, so to speak. Okay, so you will get in the attractor a fixed distribution xi of these populations. Actually, these are relative populations. So now you identify. The rule is the following: that you identify which node has the lowest population. Okay, so which firm is doing the worst in terms of its well-being. You identify that. If there is more than one firm which has the same lowest value of xi, then pick any one at random and replace that firm, replace that node. That chemical goes out of the pond. Okay, so that node, and you're left with a graph with s minus 1 nodes, and all the links of that node are also gone along with the node, and then you replace. So this is what is happening in the prebiotic scenario is that this pond is living by the side of a sea or a river or a large water body. So every day the tide comes in and it flushes out molecules from the pond, and a molecule which is low in population can just disappear from the pond. Okay, and therefore disappear from this catalytic network. Okay, and or in economic terms, the least well-performing firm is just eliminated from the network. Okay, and the second thing that the tide can do is bring in a new molecule into the pond. So this is the point where selection is, where a node is replaced is where selection is implemented in the model, and novelty enters because a new node, the tide can also bring in a new node. And this new node, being a new chemical, could be randomly connected to any of the existing nodes. It might catalyze some of the existing nodes. It might in turn be catalyzed by one of the existing nodes or not. Okay? And the same rule, the same probability P applies in choosing the new node's links with the existing nodes. So you now bring in this new node. You give it some small relative population. Okay? And then this brings you to the starting point here. You have a new network now, which has changed in precisely one node. Okay, and now this node, this system you are initializing with your old x's perturbed a little bit, and then you can now repeat the whole cycle. You ask now for this new network changed in one node, what is the new attractor for the population dynamics? Okay, let it play it out, and then identify the least populated node, replace it by a new node, and so on, and carry on. Okay, so that's the rule. The rule for the population dynamics is this, that given the C matrix, xi dot dxi by dt is given by this side. The second term actually, which is nonlinear, is merely a reflection of the fact that the xi's are relative variables and therefore they need to be normalized to unity. Okay, the real operative term is the first one, which is just linear. Okay, and what this says is that if Cij is non-zero, so let's say Cij is 1, okay, that means J is a catalyst for I, then J contributes to the growth rate of the population of I in proportion to its own population. The catalyst contributes to whatever it's catalyzing in proportion to its own strength. Okay.
Cijs are always directed. I mean, I can influence J, but not otherwise.
Yes. So if
also it can only be positive. It can be also negative. Some industries can be
yes. So you can actually run the model with both positive and negative Cijs. It turns out that largely the behavior doesn't depend very much on that. In fact, the negative links gradually decline. Okay, they don't go away, but the behavior of the model is qualitatively similar. So it's robust. The model is robust to the inclusion of negative links. Okay, and you're absolutely right that they can certainly be there. So as far as the symmetry, yes, Cij is not a symmetric matrix. In general, you are choosing each element Cij with a probabilistic rule P. So Cij you might choose to be 1, but Cji you might choose to be 0. And so in general, you will not have a symmetric matrix. But you could have some Cijs and Cjis equal depending upon the probability, the parameter P, how large it is. Yes. Equal? Which 4 processes in the previous slide? Yes. So the assumption here is that the tide comes once a day, and each time it comes in, it flushes out one molecule from the pond, one molecular species from the pond completely, and brings in one new molecular species into the pond. Each time it comes and goes, it does that. And between 2 tides, this one day is enough for the population dynamics to reach its attractor. Okay? So there is a separation of time scales. The x's are these fast variables which reach their attractor, and the Cijs then change on the slower time scale after they've reached their attractor. Okay? Yeah. Number of nodes remains fixed. In every iteration, there are S nodes. Now, you could look at versions of this model in which you would say that why just one molecule is being removed. You will remove all molecules which are below a certain threshold, and you will add, let's say, 1 or 2 molecules at a certain rate, right? You will add. And then the number of nodes doesn't remain constant. But broadly, again, that class of models has the same behavior as what I'm going to talk about. Yeah. Okay, so that's the broad. They're the rules. Okay, and the question that I was initially after is that starting from a sparse random network here, what kind of a network would emerge after this tide comes and goes many times? Okay, will something interesting happen in the pond? Yes. Sorry. Yes. Indeed, it will, and that's the most important part of the story. Okay, so I will tell you. I'll come to that. Yes. Yes. So that's basically it. And here I will. So there are some exact results that one can actually get in this model. One can show a number of things analytically about this model, but what I will talk about are some numerical simulations right now, wherein what is plotted here on the x-axis is called n, which is just the time steps, the number of time steps, okay? And number of time steps in units of graph update. So, or the number of tides that have come and gone, right, or something like that, okay? Or in the economic terms, so you can have this fast dynamics and slow dynamics. The so the Cij matrix in economic terms is really representing who is contributing to whom. So that's a kind of a technology, if you like, sort of matrix, okay, which changes on a slower time scale, and people, equilibrate, the actual wealth distribution equilibrates on a faster time scale. So, so that's the kind of thing. So what is plotted here is a property of the graph, the number of links in the graph as a function of time, and this is done for 4 different simulations in which S, the number of species, was 100, 100 nodes in the graph, and 3 different values of P here, 1, 2, green, red, and blue, P going from 0.005, 0.0025, 0.001, and this black one is actually a different run in which the selection part was excluded. There was no selection. It's a different model, so to speak, okay? But in the actual model, 3 runs of the actual model are shown with different values of P. And what you see is that, yes, initially the number of links is what you expect it to be. If you have S nodes and P is the probability of a link between any given pair of nodes, then on average you expect every node to have S minus 1 times P links on average, because there's no self loop, so S minus 1 times P. So S minus 1 times P for S is equal to 100, and say P is equal to 0.0025 is 0.25. So on average, the average number of links per node is 0.25. It's a sparse graph. Each node has, on average less than 1 link. And so the number of links that you expect in the graph of 100 nodes is 25, right? And that's around the value that it starts, somewhere here. And it remains that random value. If P is 0.005, then you expect about 50 and so on. So that's all correct. And it stays at that random value for a while. And then in all these cases, as you will see, after a certain time scale, it starts to increase, okay? It turns out that this growth is approximately exponential, okay? And then it stabilizes, it goes to a stable state with statistical fluctuations until it crashes. Until it crashes. Okay, so there are crashes that you see, and the time scale of crashes depends upon the p-value and so on, but that's what happens. And sometimes these crashes can be quite big crashes. It goes back to the random state, random graph. So here, this is what I will call as the random phase. This is what I will call the growth phase. This I will call the organized phase. An event like this is what I will call a crash. Okay, and so on. So that's what's happening in this model. And what is plotted here is in black the number of populated species. So xi is the population of the ith species, but not all species have non-zero values of xi. Some species have just 0 values of xi. Okay. So S1 is the number of species that have a non-zero value of xi. Okay, that number is small initially when the graph is sparse and random, and then it grows until it becomes equal to 100, which is the largest possible value. It fluctuates between 100 and 99, and then crashes. Okay, and then crashes, etc. Kind. So this is one of those runs, which I showed in the previous slide, is being shown in terms of some other variables which describe the system. So S1 tells you the diversity of populated species in the graph. Okay, and lambda 1. What is plotted here is 100 times lambda 1. Lambda 1 is a variable which is the largest eigenvalue of the adjacency matrix. So C, the matrix C, has the largest eigenvalue of it is what is called lambda 1, and that's how it behaves. Okay, so you can see that where this growth period starts, this lambda 1 jumps from 0 to 1. 100 means 1. Lambda 1 jumps to 1, and then when these crashes occur, lambda 1 has been declining, and here is a crash in which lambda 1 declines from 1 to 0 again, okay? And one can show that lambda 1 is 0 if there is no cycle in the graph. And if there is a cycle in the graph, then lambda 1 is greater than or equal to 1. And if there is only a cycle, a simple cycle in the graph, then lambda 1 is exactly equal to 1. So what this tells us is that this growth in fact starts when a cycle appears in the graph. And then lambda 1 grows larger, means the cycle becomes more complex, more nested, and then it crashes, so the cycles have gone. Okay. So for a longer time period, this is what happens. If you play the same run for a long time, then S1 behaves in this way. The first 10,000 time steps are what I showed you in the previous slide, and if you go to 50,000 time steps, then the same kind of pattern is repeated. And if you look at different values of S, then you see that the larger values of S, okay, the organized phase lasts for a longer time. It's more stable, okay? And I will now show you in pictures what has happened in the network, okay? So this is that same run at n is equal to 1, the initial graph, which is sparse and random. And the convention is that if a node is colored white, then its relative population is 0 in the attractor. If it's non-white, it could be blue or red or gray or whatever, then it's non-zero. Xi is non-zero. So here you have S1 is equal to 1 because only one of the nodes is colored. Then at around close to 3000, this happens, a 2 cycle appears, and this 2 cycle gets immediately populated compared to the others. And this is what we call an autocatalytic set, because A is catalyzing B, B is catalyzing A, so collectively they are catalyzing each other. It's a cooperative structure. So it's a cooperative structure between firms. That is, so you might have had independent firms doing their own stuff, but now, for the first time, a cooperative structure between firms has arisen. Okay, when this happens, this is always a stable structure, and this structure then grows. Okay, so soon after, this structure acquires a periphery. So you can think of this as a core, and this as a periphery. This structure then grows, and then quickly, this autocatalytic set basically takes over the entire pond. All the S species become part of this autocatalytic set, okay? Which is an autocatalytic set is a set of nodes, such that every node in the set has an incoming link from the same set. Okay, so that's an autocatalytic set. No such set existed here. This is the first time such a set came into existence, and then this set has grown, and with the autocatalytic set has grown the diversity of populated species in the pond. Okay, and so this is the growth phase of the network. The network then, so that's this phase, which is this part. Okay, so it is now the network. The last picture that I showed you was the network reaching here. It has spanned the whole graph, the autocatalytic network, and then it continues to grow in complexity. You can see that the number of links is increasing. The core is becoming more nested. What is the core? The core is the irreducible subgraph, the largest irreducible subgraph in the graph. And the periphery is, so if you're from irreducible subgraph, means that if you start from any of these red nodes, which is the core, you can go to any other red node. You can go to, in fact, there is a directed path from that node to every other node in the graph, any other node in the autocatalytic set, which means that there is a red node is influencing from one, through a sequence of directed nodes every other node, whereas the blue part is the periphery. Once you've entered the blue, you might be able to go to some other downstream blue node, but you will never be able to go back to the red. Okay, that's the periphery. So there is a core and a periphery structure of this autocatalytic set. And initially the core becomes larger, but then the core declines, the core becomes thinner. And then, in fact, that's the site of the first crash. At the very next time step, the core crashes. Okay, the autocatalytic set crashes. All the nodes, most of the nodes become white, and you're just left with a small set of populated nodes. And then this feature, then that red-blue structure with 3 nodes there becomes the new autocatalytic set around which the organization builds up, okay? And it builds up and crashes and so on. And here is a point where it becomes very fragile again. The core becomes very fragile again, and it crashes completely at the next time step. 8232 is this time step. 8233, you've lost the autocatalytic set completely, and at 10,000 you are back to the random network that you started with, essentially. Okay, so that's the rise and fall. If you stayed longer, then it would a new autocatalytic set would arise, and the same kind of dynamics would happen again. Okay, so the core, the core has many redundant pathways. It's nested in the organized phase, but just before a crash, it always seems to thin out. Okay, that's the case, and it turns out that if you look at all the crashes over a long run, you find that most of the crashes are core shifts. So a core shift. So you can look at the core before the crash. You can look at the core of the network after the crash. Okay, because a core is defined in purely structural terms, in graph theoretic terms. What is the largest irreducible subgraph inside the graph? Okay, roughly speaking. So you can always look at the core before and after a crash. You find that most crashes, okay, out of these 701 crashes, 612 crashes were core shifts in which the new core and the old core had no nodes in common at all. Okay, so the core had entirely changed. The internal organization which was running the autocatalytic set, so to speak, has completely changed. Okay, and in fact, if you look at the anatomy of those 612 core shifts, you find that out of them, 136 are complete crashes. Okay, they are complete crashes. So this is, what is plotted here is lambda 1 of the graph before the crash. Before the crash on this line, Cn minus 1, and Cn just after the crash. So if you look at the largest eigenvalue of the graph before and after the crash, and you classify every event in terms of these two numbers, and you ask how many events were there of this type for every core shift, then you find that a large number of them are ones in which there is no core left afterwards. Okay, and this is a keystone species has gone out, and a large number of the others, and most of the others can be divided into processes which I'm calling dormant innovations, takeovers by dormant innovations, and takeover by core transforming innovations, which I will now turn to. So, I've fortunately eaten up most of my time, so I will ask for a little bit extra time, but let me just go through this and show you some examples. So, how can one understand these events in terms of innovation, and what would one call an innovation in the first place in this context? So, here are examples of innovations that we are comfortable in calling, events that we are comfortable in calling innovation. But in the context of this model, what could we call an innovation? Okay, and I will define an innovation as an event. So a new node comes in. So which is the place when novelty is coming into the model? That's when a new node enters the pond, and that has some existing links with some of the existing nodes. Okay, and not every novelty, so that's where novelty enters, but not every such node addition event can qualify as a innovation. There should be innovation should have some kind of a performance criterion. This, it should buy something for the node, for the new node, right? And it should get something for the new node. And let's say we say that in the next attractor, so the graph has changed in this one node. If the new attractor, after this thing has happened, is such that the new node has a non-zero relative population in the attractor, then we will say that this event is an innovation. Okay. Now, okay. So if you think of this as the definition of an innovation, it turns out that all such events can be classified structurally. It turns out that in this model, such events eventually, you can classify them, and there are eventually 6 categories of such events. 6 categories of innovations. And each of these categories of innovations has a different character. Some of them are innovations which are going to cause growth, and some of the innovations are the ones that are going to cause collapse. And between these innovations that are going to cause growth and collapse, you can distinguish the ones that cause growth as some which are incremental innovations and some which are sort of more major innovations which transform the core and so on. Okay? And so let me go to, so out of these 6 categories, one of these categories is actually somewhat trivial. It is not really, it doesn't do very much to the future evolution. Okay? But so let me show you about the first. Well, this category is a random phase innovation. It's an innovation that doesn't take care of, this node doesn't take care of, it doesn't cause a new cycle to be created, and therefore such an innovation doesn't last very long. It doesn't have much of an impact. Okay. But here is the first innovation where the first 2 cycle comes into existence. And the moment, so what has happened here is that node number 90, which was earlier unpopulated, was replaced by a new node which had 2 links, one going to and one coming from node number 26. And so it formed a 2 cycle. So in the previous graph, at this time step, there was no 2 cycle, and now there is a 2 cycle. And you can show that if there is a 2 cycle, if there is an autocatalytic set in the graph, then the set of nodes that will be populated must be an autocatalytic set. All the other nodes which are outside the autocatalytic set will get 0 relative populations. That follows from the population dynamics equations that I wrote down. And that linear equation, that almost linear equation that I wrote down, had the consequence that the population vector, the attractor, is actually the eigenvector of the C matrix with the largest eigenvalue. It is in fact the corresponding eigenvector. Okay? And so you can show that this eigenvector has this property, and so these guys get populated. And what that means is that this cooperative structure, by virtue of its cooperation, is doing well for itself. And so in subsequent rounds of replacement, of selection, these 2 nodes are not going to be picked. So their relationships are going to remain intact. And therefore, that's the event that happens there. And in subsequent rounds, what can happen is that things can join this structure. Okay? The very appearance of this structure has created a one-way street, so to speak. New nodes that are replaced subsequently can either join this structure. Okay? And here is a node number 3, which this is an innovation. So this time step is an innovation because node number 3 gets an incoming link from node number 26 and an outgoing link to node number 25. So by virtue of getting this incoming link, it gets populated. And so this organization expands. So this is an example of an incremental innovation. Okay? That's the event that happens there. And here is another event where there is actually a small crash in the system. You see that there is a small crash here. And this crash is happening because of another innovation. And the structure of the node, the structure of the graph just before that crash is this. So there is this node, this autocatalytic set of 2 cycles, and it is supporting a large periphery, which is, which has downstream node links from this 2 cycle. So it's all supported, and all the other nodes which are not receiving any links from this are empty. They don't have any population. One of these nodes is, at the next time step, you have a graph of this kind, where node number 41, this node number 41, which was originally unpopulated and therefore picked for replacement, forms an autocatalytic set with node number 98 and an incoming link from node number 39. Okay? So now it is a 2 cycle which is downstream of this 2 cycle, because you can see that there is a path which is going this way. Right? There is this path. So this 2 cycle is feeding into this 2 cycle, but this 2 cycle is not feeding into this 2 cycle. And you can show that in such a situation, this 2 cycle will be populated in the attractor, and this will not be populated. So here is a node, by virtue of getting these 3 links Yes? Okay. So by virtue of getting these 3 links, it has formed a new core, and this core has taken over. Okay? So this is an example of a core shift in which you have a new competitor has taken over the existing system. Okay? So that's a creative destruction of type 1. And since time is short, I will not show you some of the other events in this category of 6, but here is an increase of the core. I will show you another example of a crash. Okay, let me just go forward. Here is another incremental innovation. So look at this event, which actually happens here. At that time step there, apparently nothing much seems to happen to the population structure. The population structure remains more or less the same. But if you look at the graph, then the following thing has happened there. You see, the graph has one unpopulated node. This node is picked for replacement, and after replacement, it forms an autocatalytic set in the periphery of this one, right? So it is a 2-cycle which is being fed by this core. This black one is the core, and this core is very strong because it has not just a single 2-cycle. The core itself is a very strong one. It has many cycles inside it. So its own lambda 1 is larger than than this one. So even though it is feeding into this one and this one is not feeding back, that core is strong enough to survive. Okay, and it supports this one. So nothing happens. Everybody is populated. Okay. So that's why there does not seem to be any apparent change in the population structure. But at a later time, so that event happened here. At a later time, you see a crash here, and that crash is because of that event that occurred earlier. And what has happened? At this point, the core is no longer very strong, it's fragile. And in this one event, what has happened is that one node inside the core happens to be a weak node. It is taken out, it goes to some other place, and now the old core, instead of having a complicated nested structure, is now left with just a single 2-cycle pointing downstream to this one. And this structure is similar to the one that was there earlier, and this causes a core shift, and therefore you get a crash. Okay? So that's the kind of event that happens. So since I've sort of run out of time, I will simply say that this example that I've showed you here is an example of another type of creative destruction. So there is a new node that has come in at an earlier time. It came in, but at that time it didn't do anything, because there was another dominant paradigm that existed that was supporting the whole network. But when that original core became weak for its own reasons, then there could be an event where this particular thing, because by itself it contained a 2-cycle, it can take over as the new core. So this is like the flourishing of dominant phyla after the Permian extinction, wherein there are many species where which there was a mass extinction, and there were certain dominant species before the mass extinction, and there were certain species which were not dominant. But after that mass extinction, the original dominant species disappeared, and the ones that were subdominant basically became the dominant species after that. So that's the kind of thing that's happening here. An event similar to the first type of creative destruction that I've showed you is occurring here in the model, which is analogous to the coming of the automobile, which causes the demise of the horse-drawn carriage industry. There is an original core which is supporting the whole thing, but then afterwards the old core becomes extinct and the new core takes over, basically. Okay, so I think I have this was a summary of the 6 different kinds of innovations, but I will simply stop with my conclusions now. That so, can one recognize an innovation on the fly? One can ask this question. You see, in hindsight, one can always say that yes, that was a great innovation. Some event or some new technology or process was a great innovation. But can one recognize an innovation when it occurs? I mean, so successful entrepreneurs sometimes can, right? That's how they recognize that this is the thing to do today, and this is going to make a change. This is going to do well, and it might even transform the system, right? So what is that intuition? What is it that works? What works has perhaps a structural content in the existing context. So what this model is suggesting is that there is an existing context which is given by the graph. In that context, certain kinds of events will have a transformative character, okay, and certain other events will not, okay. And you can actually, in this model, classify those events that will have that transformative character and those that will not. So I think I will simply stop here. Yeah. Thank you.
Any question?
Are these 6 type of innovations exhaustive or they are just examples?
They're exhaustive. Yeah, they're exhaustive actually, yeah. So this is actually a hierarchy of innovations. You can mathematically classify them structurally. And this is exhaustive and mutually exclusive classes in this model. That's all that you can have. How does one know that? Okay, so one can prove that. One can prove that all the events in which the new node gets some population can be classified graph theoretically in this manner, okay? And out of these 6 categories, 1 category is sort of trivial, but of the remaining 5 categories, there are 3 categories which cause growth and 2 categories which cause destruction, okay? Yeah.
Any other question?
If I need to know whether the dynamic equation that you have, the equation of motion that tells you the evolution of x, that is what is driving this. What I'm trying to say is that I can have a different dynamic motion equation, and then the story would be completely different if I tell you this. That's maybe completely wrong, but that's okay. But how do you defend that argument that okay, in your equation, I saw one that is when you look at the cost, the negative component, you go to the first line, the x, we're multiplying x with okay. You see, the point is that in that equation is basically higher is x, right? Higher is your xi.
Xi dot.
No. Higher is your xi dot is lower. Because your xi comes as a negative component in that equation. So your dx dt is actually negatively related with initial xi. You see?
Yes, that the second
So
the second term.
Basically,
Yeah.
if you have already grown at a high level, your potential to growth actually goes down. So people might just say, yes, this of course intuitively does not explain why you would be on a flat plateau and then you will start, but you will say, yeah, eventually when you grow at certain level, then actually you will see it is going down. What I'm trying to argue is that are there other motion equations of motion where there is something intrinsic in your calculations that give you the very interesting idea of this core innovation, the idea that essentially you grow, reach, you actually continue for a while, and then you have very intricate actually intergroup and intragroup kind of evolution and so on. So to what extent this is sensitive to specific equation of motion?
Yes, that's a very important question. So first of all, the negative term here is purely an artifact of the fact that the xi's are relative populations. In fact, if you look at the equations below, from which that equation is derived actually, there is no negative term of that kind, okay? So in fact, the only thing that you have is, so if you look in terms of the actual populations themselves, which I'm calling yi here, then the only thing that you have is yi dot is equal to Cij yj, okay? And that minus phi, that phi term actually drops out of that equation. So it's not even important for that purpose. So this is basically, that's why in fact, that apparently nonlinear equation with the second term nonlinear has an underlying linear origin. And that's why the eigenvector of the C matrix is the attractor of that dynamics, okay? So that's only appearing because, the xi's all have to add up to 1 because they're relative populations, okay? And you have to preserve the normalization, okay? So that happens automatically once you start from this linear population equation. So at the level of the population dynamics, there is no negative term. And what we have checked is that if you replace this equation by any other equation, but you keep the linear term. As long as you keep the linear term, you can keep adding higher order terms to this one. The qualitative character doesn't change very much, okay? But if you remove the linear term, and the first term that you have is a quadratic term, in particular, if that quadratic term is such as what appears in ecological systems, then the structure can change, okay? So there are particular changes that will change it, the character, but generic changes to this equation will not change the character of the overall evolution, okay? So to that extent, the model seems to be robust, okay? But, okay, so I think there are very interesting special cases that arise in ecosystems which are not covered by this. And that's a question that is actually being investigated as to what happens in such cases. And there are some interesting, yeah.
We have a theory of field destruction.
Yes.
Which actually has same spirit as what you are saying, except that we don't model it this way. For example, a farm, when let's say that in your case, the waves come in, right? But suppose you start from a situation where actually to start with, suppose a farm has grown up in its value and so on, etc. So that farm would resist a lot to get a new technology into the system because its opportunity cost is very high. Because the technology that he has invested in is, so the newcomer can leapfrog. This is a very standard kind of thing. The newcomer can leapfrog because he doesn't have a baggage. So what happens is that the existing farm, it grows, it remains, but then it resists changes and the newcomers bug it. So basically newcomers can actually leapfrog, go beyond it, and that leads to the death of that particular farm. So that
yes.
way, the cycle goes on. So again, when that other new farm becomes big, its profit goes up huge and so on, etc. It has a vested interest in the technology that it used, and so essentially this kind of new farms coming in, replacing the old farm, but again behaving like the old farm eventually. That type of story is similar to Schumpeterian idea of that why some innovation will come, and then the guy who has brought up the innovation is not going to bring out the new innovation. Somebody else will come and kill it. So this type of story goes on, but not in this kind of evolutionary detail. The thing is that what you are doing is that from the simple dynamic equation, what you can actually get a variety of possible, configurations of species, as you can call it. But part of it is kind of related to how we think about, but in a much more deterministic, much more, basically closed form solution models. Okay, so that is there in technology, in innovation games, and we call it innovation game, or technology adoption, or competition, and so on. So
yes, indeed. So that I think that's I like that remark very much, because that is even though this model is not intended really to capture that, but the sense is that it is probably in a rudimentary way capturing precisely that kind of a thing, where a new guy invents something new and takes over, because it doesn't have the baggage of the old guy, so that's what one of the types of destruction is something like that. So the question is that in a more realistic economic setting, so one can look at versions of this model which are really more, I mean, the equation that we have can be replaced by something which is economically more realistic. The graph update rules can be made economically more realistic. And the question is that in that scenario, would one also see something similar, which would then be even closer to the story that you were saying. So it would be interesting to see that, and whether one can formulate innovation in that sense. Yeah.
So you started with ER network, right? You started with your ER network.
Yes.
If your network is modular, then how the results will change? That is first question. And second, like in the equation of motion, suppose you incorporate mutualism, because in real world networks, especially in trades and in many systems, if you have mutualism, how the results will change? Yes.
So, okay. So the answer to the first question, that is supposing you have a different initial network that you start from. It turns out that the initial condition doesn't really matter. And, you can start with a modular network or a very well-connected network or an even sparser network or a very structured network. It doesn't seem to matter very much. What seems to matter is whether the initial condition has some cycles or not. If it does not have any cycles, then the behavior will be what exactly I told you about. If it has some cycles, then the growth will start right away. You will not have this initial period of stasis. But broadly speaking, after that, this growth will happen, it will reach the top, it will remain there, it will crash, and after that, the behavior will continue to be like what it was in this model, even if the initial condition has an autocatalytic set inside it, right? So broadly speaking, the answer to the first question is that the initial condition of the network does not matter, as long as the dynamical rules are the same. For the second question, the moment, the inclusion of mutualism will require higher order terms in that population dynamic equation. And the answer is related to what I had said earlier, that if you are looking at an ecological setting, then the linear term, the only term that I have in this equation, which is the linear term, will actually be absent, okay? And you will have quadratic or higher terms in that equation. And then it turns out that the dynamics is not like this, okay? There is some interesting dynamics which can be probed that way, something that is going on, but it changes the character. But if you include mutualism, but retain the linear term in the dynamics, then it doesn't change the character because you're including a higher order term, keeping the lowest order term still intact, you're not taking it to zero. If you do that, then it doesn't change the dynamics very much, okay? So that's the answer to your question.
I wanted to ask, you said you tried C is equal to 1, 0 as well as -1.
Yes.
So how does not, like, C is equal to -1 would correspond to something growing at the expense of another, or like something causing the other to
inhibited. So Cij is equal to 1 means that the presence of J will cause I to grow in population. Cij in -1 will mean that the presence of J will cause I's population to decline, right?
Like, is there no qualitative change?
So I will tell you what happens. What happens is that you can now, let's say you start the initial network with a probability P of Cij being non-zero, and if it is non-zero, with equal probability it being -1 or +1, right? So the sparseness of the graph is as before, but the non-zero links could be either positive or negative with equal probability, okay? And your update rule also, each time a new species comes in, you can say that its links are chosen with probability P to be present or absent, and with probability, if they are present, with probability half to be +or -1. Now, if you do that, what happens is that you will occasionally get cycles with negative links, right? You will get, in the random phase, the number of positive and negative links remains the same. But there is a fundamental difference between a -2 cycle and a +2 cycle, or a mixed 2 cycle, right? It's only the +2 cycle which is a cooperative structure and which is more stable in this environment. It's only the +2 cycle which endows the members of the two cycles with a large population. If one of the links is negative or both the links in the cycle are negative, then that autocatalytic set is not really an autocatalytic set. Collectively, they will not do well. So what happens is that those structures do not do well. It's only a positive cycle that gets picked out, and that becomes the seed around which the system self-organizes. Cycles with negative links are not preferred. And so, over a long period of time, what you find is that this same dynamics goes through. You still have a few, because randomly negative links are being generated all the time. The system still has non-zero number of negative links, but broadly the autocatalytic set that survives is the one which is coming with positive links. So there is, what happens is an asymmetry between positive and negative links gets created. The symmetry gets broken by the dynamics. Yeah, that's what.
But they would still, at least intuitively, be different kind of what you were calling the destructive, as in
Creative destruction.
creative destruction.
Yes.
That the number of the kind of events in creative destruction would probably change, right? Like possible kind of events in that.
We haven't actually analyzed the, this theorem that you have exactly these 6 classes. That theorem only has been proven for the 0-1 case. For the 0-1-1 case, that has not been proven. And perhaps it needs to be looked at in more detail as to whether that classification holds. All I can tell you at this juncture is broadly the nature of the evolution, short term and long term, remains the same. Okay. Yeah.
Any other question? I want. So for Cij, we are considering 1 and 0. Instead of 1 and 0, if we consider H-side function using some thresholding and dynamically we are changing, then can we get phase transition behavior in this network?
We have not tried that. What we have tried is that instead of checking it between 0 and 1, you choose, if it is non-zero, you choose the link strength to be randomly between 0 and 1. You can have a weighted network. We've tried with a weighted network, and again, the model is quite robust. It doesn't matter whether you work with a weighted network or whether you work with just 0-1. The qualitative behavior is essentially topological, and here in this model, and therefore doesn't change very much. But we haven't tried precisely what you have suggested, so I can't really give you an answer to that one. Yeah.
So let us.
I have one last question. Just if n is not fixed, like the matrix is not fixed, if you have remove one edge and you put 2 edges at each time, then how it will behave? And number of edges.
Okay. Do you mean the number of edges, the number of nodes?
Number of vertices.
Number of vertices. Yes. So yes, you can have a rule like that. And then what happens is that unlike in this model where it goes to a fixed number 100 and then reaches a stasis, instead of that what happens is that it goes to a certain number, it fluctuates around that. It still reaches a stasis, but that is there is a fluctuation, there is a greater fluctuation of the number of nodes, but the overall dynamics seems to be the same. Okay.
Whether the crashes will be more or just there will be no crashes.
There will be crashes. There will be crashes. The crashes, their numbers don't change very much. Okay. Yes. Yeah.
If there is no question, then please thank Professor James.